Most of us picture the Milky Way as a perfectly flat, horizontal plate spinning quietly in the dark. Earth hurtles around the sun at 30 kilometers per second, while the sun whips around the galactic center at 250. Our system is tipped 60 degrees, bobbing through the disk every 60 million years. Zoom out, and the galaxy is dragged by the Shapley supercluster. Trying to map the shape of the Milky Way from right here on Earth is like trying to take a clear photograph while sprinting on the treadmill. Our own complex, layered motion is constantly blurring the data. When astronomers observe other spiral galaxies, they often see the outer edges bending or warping. Naturally, they want to measure if our own galaxy has that same bend. To figure this out, researchers use two main techniques. The first is geometric measurement, which means plotting the physical coordinates of specific star clusters in 3D space. The second method is dynamic measurement. It tracks the star's angular momentum, the arcs of their orbits through space. But when compared, these two datasets showed a discrepancy. The physical shape of the star clusters did not align with their orbital paths. This chart tracks the tilt angle and orientation of these stellar orbits. The variance in these data points suggests the galaxy is precessing, or wobbling, at speeds that exceed theoretical limits. When observational data breaks established models, it usually means a variable is missing from the equation. We were calculating the galaxy's shape using a flawed understanding of our own local reference frame. That missing variable turned out to be right in our cosmic backyard. The section of the galactic disk immediately surrounding our solar system has a slight local tilt. This local neighborhood is angled by just 0.6 degrees. Because the sun is moving through that tilted space, it picks up a vertical velocity that astronomers hadn't accounted for. Specifically, the sun is drifting 9.4 kilometers per second vertically relative to the galactic midplane. That motion was acting like a subtle camera shake, distorting measurements of the wider galaxy. Subtracting that 9.4 kilometer per second vertical motion from the data brings the geometric and dynamic models into agreement. Accounting for the precise anomalies of our local reference frame is the only way to accurately map the larger galactic architecture. With the sun's vertical drift properly removed from the equation, the extreme wobbling of the galactic disk disappears from the models. In its place, the corrected data reveals that the Milky Way's warp is actively flattening out. Astronomers project that over the next 100 to 200 million years, the crease of this bend, the line of nodes, will stabilize. The Milky Way behaves as a flexing environment, responding to dark matter and satellite galaxies. We are watching the disk slowly recover from external pressures. Understanding this grand, recovering structure was only made possible by first turning the lens inward to measure our own turbulent motion.